Hi everyone, this is lab number 7, which is talking about the shear strength of sand. Generally, when you say shear strength of sand, we are saying about the frictional resistance of the soil. And it is basically governed by an equation called a Columbus equation, which is equal to the shear strength of the soil is dependent on the normal stress applied on the soil, on the friction angle of the soil, and on the cohesion of the soil. Since we are dealing with sand, we assume, or in practical sense, the cohesive nature of the soil is 0. So for the determination of shear strength of sand in the lab, we do a test based on an equipment called a direct shear test. So generally, for our today's test, we have two samples. One is the Ottawa sand, which is a natural soil, and the other is a crushed glass. The first activity we need to do is to determine the angle of repose. For that, what we do is we take out some soil sample and we pour it over the table very carefully. So as you see, it forms a kind of cone shape. This is basically because of its frictional behavior. And generally, the angle that it makes with the horizontal is generally called angle of repose, and it is roughly related with the friction angle of the soil. So you use a protractor to determine the angle of repose, and later you compare it with the result from the direct shear box test. Okay, this is our test setup where the normal load is applied through this vertical part and the horizontal load is applying through this one. So this is the box where we are going to put our sample, and this is the specimen box where it is split into two, like this. The reason that the specimen box is split into two is because, it is a direct shear test. So the soil is sheared when the bottom one stays at one place and the top one is pushed sideways in order to create a forced shear plane. So the first thing we need to do is we put a porous stone over here and we fix this one with the black screws at the place in order to keep the sample at the right place. And then remember that we need to take the weight of the sample and the bowl before we put some of our sample onto it. And we don't have to fill the soil till the top part of this one, and there is a black mark over here where we need to fill the soil. You have to do this very carefully in order not to lose your soil. So once it reaches to that mark, you have to measure this one in order to know how much soil you added onto it. Then once you do it, we have a spacer. You have to create a level and tamper it a little bit. So that you'll have a well-trimmed sample. Then on top of that, you put your porous stone carefully on that leveled surface. And you take this one to the box. Then once you have the box, you put it perfectly. This side should be on the right side, and since this one is a very sensitive machine, you need to be careful when you place this one on top of that. And then you have a load cap. You put that one like this, and this one is the final one where you need to put your this is actually a little bit closer to this one, so we need to bring it a little bit up so that we can make adjustment on the level. Then the next one is, this is called a reaction ring, which connects this part with our sample. So make sure that all the bolts are tight enough to make a good grip with the sample box or specimen box and the horizontal loading part. Make sure that everything is tight enough. So once everything is set like this, you need to bring down the vertical load to 1/8 of an inch, to the level of 1/8 of an inch, and bring this one to make this one leveled enough before you start your test. Once you collect your data from the machine, then the first thing you'll come up with is a plot of the shear stress and the shear strain, and you'll get such kind of curve roughly, where for example for 3 different tests with load of 50, 150 and 100, and from this you'll get the maximum or the peak strength of the soil and the residual strength for each point. And in your another plot you'll have a shear strength versus a normal stress, and from the 3 tests you get 3 points where you can plot the failure envelope. This is generally, when you say the failure envelope, beyond this stress, the soil can no longer exist or can no longer take the load. That's why it is called the failure envelope. And from this failure envelope, we get from the slope the friction angle for the peak stress and for the residual one. And once we have the failure envelope, we can come to a concept of the Mohr circle that we will discuss in the lecture in detail. Using that point, we'll have stress Mohr Coulomb, which is called the Mohr circle. You will discuss this one in detail in your lecture.